Good morning, Professor and fellow students. My name is Huang Yishi. I'm currently doing the summer intern at Nano Engineering Department, and my supervisor is Chen Shi. My topic for today is stretchable ultrasonic transducer array for three-dimensional imaging on complex surface, which is basically discussing about the preparation of and applications of these novel wearable ultrasonic sensors. I will divide my presentation into 5 parts. First, I will introduce the characteristic and the applications of the ultrasonic sensors. Therefore, you will be able to obtain some basic concept of these amazing devices. Secondly, the material and the method I used to fabricate the sensor and also the optimizations of the fabrication process that I've done. Thirdly, the result of the fabrication process and the optimizations that I have achieved. Last but not least, the sum up of my research project and the references included in the presentations. So for the introductions, the traditional ultrasonic probes always have this hard plastic cover, which make it rigid and unstretchables. So rigid probes cannot achieve a solid interface contact with the complex surface, such as human skin, and therefore the air gap between this interface lead to a large acoustic energy reflections and wave distortion, therefore creating an unreliable test results and a low visibilities. On the other hand, the sensor that designed by the research group is soft and stretchables, allow the devices to work on a non-planar complex surface. With these unique properties, the devices can obtain three-dimensional images on complex defect surface. So for the sensor compositions, mainly the sensor have 5 layers. The bottom electrode with polyimide is an electrical conductor used to make contact with the non-metallic part of the circuits, and it also provides energy for the transducers. So for the piezoelectric elements is an essential part for the probes to generate ultrasonic wave and also to receive the reflections of the wave. So basically it serves as a transmitter and receivers. Among the several types of piezoelectric elements, piezoelectric symmetric is the most common use and also is the one we use in the lab. The next element is a baking layer. The baking materials is located behind the transducer to prevent excessive vibrations. Reducing the excessive vibrations is able to improve the resolution in the image. So for the top electrode, it has this unique island bridge systems. Each island holds a rigid element. The bridge can unfold to accommodate the external applied strengths. Therefore, the metric is rigid locally but soft globally, which is one of the main reasons that the device is extremely flexible. Last but not least, the silicon elastomer is a non-reactive and stretchable elastomer, and it is resistant to extremely environments which provide a perfect protection for the circuits. So let's move on to the method. The fabrication process can be dissected into 8 steps. So first of all, we use the software to draw the ideal patterns and use a laser cutting machine to ablate the pattern on the copper sheets. And the electrode pattern will be transfer printed to a separate EcoFlex substrates, and the AFC cable will hot press on the electrode to serve as their connection access for data communications and power supply. Next, the solder paste will be used to serve as a linkage of the transducer and electrode. Later on, the transducer will be implanted on the electrode and the bottom electrode will be transferred right on top of the transducers. Last but not least, the silicon elastomer will be used to cover the entire circuit for 2 hours until it's fully dried. And for the sensor optimization, as we can see in the picture, this is the sensor that we have discussed before. And to zoom in the sensors, we can see there's actually 2 parts, which is the electrode and the AFC cable. However, the linkage between electrode and AFC cable is actually physical bondings, which is kindly weak and easily to break down, which lead to an open circuit. And the solutions for the sensor optimizations is put the solder paste between the electrode and AFC cable. So we alter the property of the interface, provide a chemical bonding of the electrode and the AFC cable so that the linkage will be increasing. So for the result, this is a sensor designs for the blood pressures and the laser ablations gave a clear cut of the patterns. Next, the pattern was successfully transferred to the glass slide and a hot force was applied to bond the electrode and the AFC cables. Later, the solder paste was cemented on the electrode to link the transducer and the electrodes. As we can see, the transducer was implanted by using a mold, and the top electrode was put it on right on the top of the transducers. Last, the elastomer were applied and to cover the entire sensors. For the sensor optimizations, instead of heat press the AFC cable directly onto the electrode, I first add the solder paste to the electrode to alter the property of the interface. And I heat up the solder paste to solidify the solder paste and heat press the AFC cable later on. In this case, a chemical bonding based optimization is demonstrated. And for the outcome, for the sensor fabrications, a single transducer were used to detect the pulse. As shown in the picture, the vibration is the pulse from our vein. And this is the sensor I use. And for the linear transducer array that I also fabricate can be also used to detect the pulse. And so for the conclusions, I fabricate a high quality transducer array for the research. However, I take the sensor to the next level. I successfully develop a unique method for sensor optimizations, which enhance the performance of the sensors. And this is the reference that I've read. And thank you for your listening.